Hi, Bernd.
Okay. Hi, how are you?
I'm fine. Thank you for accepting my invitation.
Well, you're welcome. And you were a very good one of my customers. Therefore, I have a very good remembering working together with you. And, in the last 25 years, we got friends all over. And yeah,
Yes.
I'm looking forward to see you again next month, by the way.
We will. Yes, because one of the reasons why I would like the timing for our talk now is that the Danish Magnetic Society are arranging a workshop or a small conference in Denmark, in Hobro, near Syntex, where I work daily, at the 14th and 15th of November.
Yeah.
And you are also invited as one of the speakers. So this could be an opportunity for you to give some preparation for the show.
Yes, thank you very much for the invitation. It's of course a honor, even being not a Danish one, to speak at the society there. I did it, I think it's about 10 years ago, when we had a meeting together at Syntex, as I remember right. Yeah, long time ago. That was a time when I was with MagnaQuench. I'm some people say I'm retired, but I'm not. I have the feeling I'm more busy than I was before even. I'm working now for my own company, as you know. And by the way, we did found a new company last week, 2 friends and myself. Yeah.
Okay.
And there we want to bring in some new activities. I'm working beside my work as a scientist and researcher, where I support companies still as a consultant. But the new activities are that there will be a new resource for rare earth materials in India. We will talk about later, I'm sure, a little bit more. And one of these companies from India, they get notice of my name. I don't know because I'm not very popular, I think. But however, they did ask me if I would support them in technology. And after some weeks working together, and both sides were okay with each other, they did offer that we will overtake the sales business for Europe for them. And therefore, I hope that during next year, next year, we will offer rare earth materials from India, not from China.
Sounds interesting.
From the very beginning, that means from mining to the magnet, it will come from locations outside of China. And the other activity is, we talked before about this too, the samarium iron nitride. For me, this material is a very popular one in some countries, but not in Europe for whatever reason. And there are so many advantages from cost, sustainability, environmental, magnetic properties even, and so on. It's just a little bit more complicated to make these magnets because it's anisotropic. And that's a hint for many people.
Before we go too deep, I would like to have your background history, because you are in fact one of the pioneers in rare earth magnet. So how did you get involved in the magnet world?
Well, it's so long ago that I even don't remember. No, I'm joking. I was a student at University of Stuttgart, and I was in an engineering education, and I did, after the first diploma, it's now called bachelor, but at these days it was the first diploma, I decided to go for material science as an engineer. And I got an invitation from the Max Planck Institute to work as a student in their groups, because I had a good understanding in the lessons I did join from a professor there. And yeah, and that was 1983. It's about 40 years ago.
Yeah, and the magnets, the rare earth
And
magnets, they were invented in
1982.
Yeah.
And therefore, that was a circumstance that there was European money available for research work. They wanted to bring into the European science the magnet world, which was at these days covered by Japan and USA. You know, in Japan, they had this Sinterwood, Sagawa, did work it out. And in America, they made the jet casting and the rapidly quenched materials for MagnaQuench.
Yeah.
MagnaQuench was founded later, but they did develop the bonded materials. Yeah. And that was in 82 when the new patents came up. Some groups were working since the 70s of this, and it's very interesting. I did find a paper from Ukraine from 1978 where they did investigate the neodymium iron boron system, and they did even identify this magnetic phase.
Okay, but they didn't measure the magnetic properties.
No, that was the thing. And later on, when I was really interested in what were they doing, and I had the opportunity to meet one of these scientists from Ukraine, Professor Bodak, a lady. She told me that they did see that there was a magnetic material, and they did identify the 214-1 phase even, and they had micrographs of this.
Whoa.
But they were not able to determine the magnetic properties because there were material scientists just and not magnet people. And therefore they gave it away to another institute in Russia, and they did not follow up.
Okay.
Can you imagine if Russia would have developed the neodymium iron bone material in 1978? What a different world.
Yeah, it would have been very different.
Yeah.
And
well, there it started in 1983. I came there as a student, and I had to make a literature research because nobody of these scientists there were familiar with magnet materials. And that was a startup, And I made my diploma in 1986 on neodymium iron boron there, and then they did invite me for a PhD work on neodymium iron boron again, on the influence of other materials. Diploma was on the heavy rare earths, then corrosion resistance, temperature stability, and so on. All these basics in the 80s were in our focus. And after 4 years of PhD in 1990, I did move to industry.
And if we could dig a little deeper into the material science, could you describe a little what is it that makes this neodymium iron boron magnetic? Can you describe with words how you can define this magnetic in a microstructure?
Well, the very special thing of neodymium iron boron is that there is a magnetic material, mainly iron. In volume percentage, it's more than 80% is iron. Even it's always listed as a non-iron material. However, it is iron. And the magnetic properties are coming from iron. But iron has a structure which is cubic by nature, and therefore it's isotropic. It has the same properties in all directions. And with the neodymium you can make a new design of the structure. You know, the rare earth elements, the atoms are huge atoms, heavy metals. Neodymium has the atomic number of 100 or atomic weight of 145, as I remember right. 3 times of iron. Yeah. Therefore, it's a huge atom. And to make the iron, which is still carrying the magnetic properties, anisotropic, which means it is not demagnetized so easily, you have to pull the iron atoms in a bigger distance and not in all directions in the same way. And that is the trick with the rare earth. You place the big atoms into the iron grid, and you have fully new magnetic properties because the iron to iron distance is enlarged and not symmetric anymore. And that makes it so special.
So,
therefore,
so the magnetic properties are iron, and if it was pure iron, you would have a saturation level of around 2.
Yes.
But because you dilute it with these additional alloys, you can never reach 2 in a neodymium iron boron. You could reach 80%, so that's 1.4, 1.5. Yeah, 1.6. Yeah.
Yes, exactly. It's so simple.
And boron, what does that do inside?
Boron is a stabilizer, let me say. That is a constitutional thing. There is no magnetic function of boron at all. But to make a ternary phase with this anisotropy in the geometry, you need the boron. Otherwise, it is, from a thermodynamic point of view, not stable. You have many binary neodymium iron phases, the 217 and so on, but all these phases does not have these special characteristics. Therefore, it is just to make a ternary phase, and this is working, by the way, from the phase character. The same with oxygen you can use, with carbon you can use, with nitrogen you can use. That is the fascinating thing with this rare earth. You can make it from the iron, you can make it from the cobalt, and even from the nickel, this phase. And you can make it with all 16 elements of the rare earth. And you can make it with boron, with carbon, with nitrogen and oxygen. Therefore, 3 cross 16 cross 4, that is the number of variations you can make of this phase. And the best thing is, it's most time fully mixable with all elements. Therefore, from this 100 and something different variations, you can make hundreds, thousands of variations by mixing different atoms together.
So the use of the cheaper cerium, praseodymium is just a dilute to dilute it and make it cheaper.
That is
you
one
can
way.
Mix it in instead of neodymium.
The other way is, or the other intention is, of course, to make a variation in properties. You can increase, for example, not only the magnetic properties, like corrosivity with the heavy rare earth. You can make very interesting effects, for example, with cobalt on the corrosion side. As we have in the combination of iron and cobalt in steel. And that are effects working there in the, not the same way, but in a similar direction.
Therefore, how much cobalt do you need to make a corrosion resistant?
Well, the normal use in sintered materials is in the range of 3%.
Okay, so not that much.
No, but it works. But the effects are very, very complicated because there is the microstructure of these neodymium bone magnets. I always say neodymium bone, just it's much more than just neodymium bone. Like a steel, it's not just iron and carbon.
Yeah.
But with these additions, you can influence the microstructure. Yeah. And the microstructure is very important on the mechanical properties, on the chemical properties, and last but not least, on the magnetic properties. Yeah. And therefore, it's
and the microstructure. It comes from the processing route.
Yes.
So can you make these alloys with traditional melting casting, or do you have to go the powder metal route always?
You can make the normal casting, of course, but that's not a magnet anymore, or not a senseful magnet. It is a magnet material, but you are losing your magnetic anisotropy in a certain way just by cooling down. And you need the powder way then to make it anisotropic again. And the other thing is that your grain size is becoming too big if you cool it down in a normal book mold manner. Yeah. And therefore, if you have big grains, your coercivity is very poor. Yeah.
So the only route is powder metallurgy and rapid quenching.
No, there are much more ways. That is the wonderful thing of metallurgy. You can get very interesting results by processing variations. There is, for example, the samarium iron nitride as a very good example. You know, samarium is very hard to handle in a process because that is the only element, by the way, which is not liquid at room temperature and normal pressure. There is no liquid phase available. Samarium is going from the solid state direct into a vapor state, gases. Yeah.
At what temperature does that happen?
This is in the range of around 1000 degrees.
Okay.
Yeah,
not that
it's
high.
solid until this, and then it's just evaporating.
Yeah.
And you can imagine that alloying by melting, if you don't have a melt, it's difficult. No, it's really, the periodic table is so fascinating in the special things. Yeah, we have only very few which are liquid at room temperature. Yeah, like quicksilver.
Yes.
Gallium is very close to, it's melting at 37 degrees C.
Okay.
Yeah. And so on. Most are solid or gases. But they all have a liquid phase, but not samarium. And therefore, maybe you know the Goldschmidt process, maybe not under this name. It is a core reduction of materials. It's used today for making railroad tracks, for example, for molding together the different parts of the steel. And this process is a process where you create a very exothermal reaction, and that brings you the high energy you need for. And it is take an oxide of a material like samarium oxide, mix it with calcium, and activate it. And then the calcium will reduce the oxide, taking the oxygen away. And the rest is a metal. And if you have the samarium metal,
the Kroll process, it's used for titanium production as well.
And if you then offer iron in addition to this reactor,
Yeah.
the samarium is immediately reacting with the iron and making a samarium iron alloy.
Okay.
And that is, for example, used for samarium cobalt magnets. Yeah, samarium iron nitride, it's the same because that's a derivative of samarium cobalt. It is used, for example, for the heavy rare earths. Yeah, it is very complicated, very difficult to reduce the heavy rare earths from the oxides to the metal because you need high temperatures. But with this process, you can make a pre-alloy with iron and, for example, dysprosium or terbium, which can be used directly in making an alloy.
Yeah.
And if you have, for example, a samarium iron combination, you can make it liquid.
Okay.
Yeah.
So you can
That's a
heat
big
it
advantage.
to make it liquid. Yeah.
Yeah, that's a trick.
Yeah. To the history of making neodymium magnets, I also remember there was a process called HDDR.
It's still alive.
What was that about? It's
still alive, yes. That's
okay.
another very interesting behavior of these materials. You can imagine if you have a crystal cell as a combination of very big atoms and smaller atoms and very small atoms. The boron is very tiny.
Yeah.
Yeah. Therefore, you have a lot of free room in this cell. Yeah, because it's a normal one. You have space in between the big balls. Let's talk about balls. Yeah, the big ball and smaller balls, and therefore there are spaces in between.
Yeah,
and we call it tetragonal space and so on, depending from the geometry. You remember from your lessons at university, I'm sure.
I do, yeah.
And this material has a behavior that you can dilute gases inside. Yeah. And that is the storage, like hydrogen.
Yeah.
Yeah. And the people did see that neodymium iron boron is a very good hydrogen storage, by the way. There are even patents from Sumitomo to use it as a hydrogen storage.
Okay. Yeah.
And a side effect is that the dilution of the hydrogen in this material does create a volume effect in the material, because the surfaces of the other atoms are reorganized in the relation to the hydrogen, and therefore it's a very small volume expansion created.
Yeah.
But this small volume expansion is causing a lot of micro scratches.
Cracks.
Yes, cracks. Thank you. Yeah, and therefore you make from the solid metal, you make a powder out of it, because you can break it very easy. It's very brittle then, a lot of cracks. You can mill it much more easier, and that is the effect. And the other thing is, with this hydrogen inside, you have a deorientation. The material is breaking away, and you are creating some other phases by this in reaction with the hydrogen and temperature.
Yeah.
And you go into a particle size which is so small that you can use this for anisotropic materials. Because with this particle size, after reorganization, going down to a certain temperature, the particles are smaller than the domains are. Therefore,
okay, so it's single domain.
You have a single domain, and you can use then this material as anisotropic material. But then after recombination, it's a neodymium iron boron again. And if you then pull off the hydrogen, you have an anisotropic powder.
Yeah. Mm-hmm.
Yeah.
And that powder will then be mixed with a binder or lubricant, and then you can press.
You mix it
magnets.
as the isotropic neodymium iron boron together with powder. The additional step you need is the orientation of the material during your form giving process. Yeah, and then you have an anisotropic magnet. Unfortunately, the corrosion resistance of these materials is very poor because of the micro cracks. Therefore, you did create a big surface inside the material. And that makes it very sensitive. Therefore, you have to work with this material in a very protected environment.
Okay. Yeah. What about sintering? Can these materials be sintered or?
No. All these materials which are using hydrogen or for some iron nitride, the same with the nitrogen, these gases are diluted in the material and they disappear at a certain temperature. And this temperature is always below sinter temperature. Therefore, before you have the opportunity to make it dense by sintering, you lose it.
So what is needed for a magnet to be able to be sintered?
We call it liquid phase sintering. Sintering in this case is just bringing all the powder particles together, that it is a solid state in a most dense form as achievable. Because with the powder you have a density of 3 or 4. If you sinter it, it's a strong shrinkage during sintering, and you have a more dense material. And therefore you need, for the shrinkage phase, we call it liquid phase sintering even, which is getting liquid at a certain temperature.
And this phase, that is
it's the grain boundary
why
phase.
You have a little extra of neodymium in it typically.
Well, if you go to the pure ternary material, neodymium iron boron, it is more or less the pure neodymium, because if you cool down, you have your series in solidification. First is the iron, then the 2-14-1 phase, which is formed out of iron and liquid in a reaction. And the liquid moves on into a eutectic. Therefore, with lower temperature, the phase relation is not changing anymore quantitatively. It's changing, but it's still liquid, and iron is reacting to 241 until all liquid is disappeared. And this liquid goes away in a eutectic, as always. As always. And the eutectic is out of 214-1 and pure neodymium and a ternary phase, but this amount of this other ternary phase is neglectable. Finally, you end with the normal compositions in a relation between 214-1 and neodymium, and that are the two phases in your microstructure. And the neodymium eutectic is solidifying at about 620 degrees C. Therefore, you have to cool down a certain long way until all of the liquid is moved to solid. It's going less liquid, and then it's disappeared.
And because typical sintering temperature is around 1150, 1200, isn't it?
1100. 1100 is a good temperature.
Okay.
And it's as I said, it's a long way down.
Yeah,
and
absolutely.
the main thing is the microstructure of these magnets. Now, the magnet characteristic, it's depending from the surface of the grains. Yeah. If the surface of the grains is very smooth and homogeneous, it's a good magnet. Yeah. Because if you have faults or misalignments in the surface, disturbance of the chemical cell, then the demagnetization can start preferred at these points. But if it's a smooth surface, you have a very good shell for your magnet particle, and the demagnetization cannot start because it has always to start at the surface. Yeah.
Okay. That
And
makes
then
it
you have a lot of
stronger
time
magnet.
for healing the surface. Yeah.
Yeah. Okay. Bernd, let's jump into application, because this podcast, the name is Everyday Metallurgy, so it's more to introduce to people where metallurgy is used in your daily life. And I know it's very easy for you to describe where we can meet magnets on our daily life. I know you used to take up your phone and say, "Oh, in that one, you have."
Sure.
I'll guess maybe 7, 8, 10 magnets in a
Yes.
car. How many magnets do you have in a modern car today? Do you know that?
Well, it's depending from the sort of car.
Yeah,
If
I
you
have a very modern car.
well, you can have up to 100 magnets in your car. Yeah.
Yeah.
And you have many applications. One of the big advantages of these neodymium iron boron magnets, they are very strong, and therefore you can reduce the size of the magnet. And by reducing the size of the magnet, you can reduce the size of your application. Therefore, your motor you are making out of it, it's getting smaller. And smaller means less weight. Less weight means less consumption, higher efficiency of the car, and so on. Therefore, many cars prefer to use neodymium iron boron magnets in many applications. If it's a very small magnet and it's sensitive to cost, they are using ferrite magnets. But even there, most are anisotropic ferrite magnets, therefore quite interesting materials too. But you have your window lifter motor, you have your screen wiper motor, you have your seat motor, you have your steering motor, and so on. So many motors, and all these motors, they need the best efficiency you can achieve to reduce weight. Otherwise, you have a locomotive weight.
Yeah.
If you have everything without magnets. And one of the very interesting statements from Sagawa, who was the founder of the sintered neodymium iron boron magnets finally, he said, we have more than 50% of our energy consumptions in motors and similar devices. And if we use more rare earths, we are able to save the world by this.
Yeah.
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 It's really, it is, I think in your own experience with your company, these circulation motors, for example, yeah, pumping the water through the heating system, it's, yeah, you saved 80% of the energy in your pumps by using neodymium iron boron and a well-controlled, intelligent system, and that's a huge difference, yeah? If we would exchange all the circulation pumps in Europe just by the new technologies, instead of the old ferrite with no electrical control and so on, we would save several terawatt hours every year. That are several nuclear plants just for this application. Therefore, and amazing. That is with all the other applications in the cars I described. Creating energy, wind power. Wind power is our big hope for getting the energy. You in Denmark are much more informed than many other countries. And in a modern offshore wind cabin, you have about 4 tons of neodymium boron. 4,000 kg to keep this big generator running and creating electrical energy. That are the big applications. If we imagine that we hopefully have about 40-50 million electrical cars in the future, you need 2 to 3 kg for these engines for every car, which is not so much. But if you have 40 million, it's 2 kg, it's 8,000 tons.
It's a lot. And that leads me to the next subject, because it's not a secret that today or over the last many years, the market of rare earth has been dominated by China. And will that continue with this expansion you just explained, in both in energy generation and in our cars running on batteries and magnets? Where should we get all these raw materials from in the future?
Good question. That is one of the main items I'm interested in, because this is the key factor how we can organize our future with these magnets. We have in the moment very dominating China, and they have developed their mining and their manufacturing processes in a way that all the other countries are buying from China, because it is the cheapest way. They can produce it. They do not have all these environmental problems the same way as we have. They do have a lot of mining there. In China, it's often a byproduct. Some of the mines, they are getting out iron, and the scrap they don't need. There is the rare earth in, therefore they just have to collect it from the scrap hill.
From the slag piles.
Therefore, they have everything. They have the raw material, they have many people, they have built up all the manufacturing, and the other countries, they were too lazy, and they did not spend more money than necessary for these products, and everybody is buying. As a result, 90% of the magnets are coming from China. We hope that we can change this. There's enough raw material. Rare earths does not mean these materials are rare. Not at all. No, they were rare for Europe when the chemical engaged people in the past started to develop. You just did find it in some regions in Scandinavia.
I heard. I don't know if it's a Swedish story, but I heard that it was a Swedish guy who first found it. The heavy materials at the bottom of the periodic table, and they were behaving different. And in Swedish, to be different is sällsam. And when he introduced Germany, he introduced that to other people in other countries, sällsam became seldom. And seldom is
and in English it's seldom and rare. Therefore, these words are very similar. Of course, depending from the mixture of these ores, the rare earths, there's more or less neodymium in, or more or less cerium, and so on. And because all these elements have different melting points, for example, the melting point of this solid solution, you don't identify it as a multiple of elements. It's behaving like one element because they have full solid solutions, statistically solutions. Like you mix water with something in, and then you have a new liquid.
So it behaves different. That was
It behaves different. And that's exactly the same in solid state if you have all these different materials. Therefore, they are seltsam in German, same as in Danish, but they are not rare. They are all over the world. These elements were formed when the stars were formed. Because these big elements, you need a huge pressure and a huge heat to form it. And even in the middle of the earth, it's not enough. You need a sun to form it. And that was a long time ago. It was created. But the earth is part of a sun. And in the middle stayed liquid. And if you have a volcano, it's going out from the middle. And then you find it. And you find it at all different locations all over the world. And now in India will be the next big country who will offer it. And it will be a competition to China, of course, because their volumes are very high, tremendous. Millions of tons of rare earth are available from there, and they can put it from the sands at the beaches even. Very easy. Just collect it. And therefore, there will be something new in the future when India will come up to this market. As I started our exchange, India will change the world again in this field, and it will take back shares from China, very clear. And if you are looking that the total volumes in China are still increasing, but the shares of the global part they are taking is going back because Australia is increasing, America, Mountain Pass is increasing, and there are new locations in Thailand, in Myanmar, and wherever where you find these rares because they are globally available.
I even heard in northern Sweden they have found a quite big ore.
Yes, And the lack in the next 10 years will not be the raw materials availability. The lack will be in processing. Because we will need tremendous volumes for the wind power, for the electrical cars. And we do not have enough process technology. And we have by far not enough technology here outside of China, for example, in Europe. Now, MagnaCrunch is building a new plant in Estonia, making rare earth magnets, which is beside Vakuumschmelze, the first one who is concentrating on automotive, for example, which is not the business of Vakuumschmelze because in Germany it's too expensive. We are always competing against China, and China is so cheap in manufacturing. We have no chance. If there is not a strategic interest and the people are willing to pay for, we have no chance. That's it. And therefore, the world will change in the next decades, very clear. And we will find India as a partner, maybe for Europe, to build up new relations. And if we are doing our job well, then we can use it for our advantage. And some competition is always good on the other side. And the geopolitical situation in the moment sorry, will help to get, if we are the ability to get a little bit more distance to China.
Yeah. Ben, I have a last question. Then I think we have spent our time today. It's about it in Europe or in Western countries. Today it's very modern to talk about recycling or circular economy. How do you see recycling potential of rare earth magnets?
Well, the potential fundamentally in a technology way is given, but we must understand that the rare earth materials are very different to most of the other elements in our periodic table. They are forming oxides, and the rare earth oxides are the most stable combinations of elements in nature. Therefore, if we want to get the metal, it's always a huge energy spending to break up these intermetallic compounds or oxides and so on. Therefore, you need a difficult process. You need a lot of energy. And if you want to make it from recycling, it's getting really complicated because you cannot use the different elements all together. You need the separation. And if you are collecting used magnets, they have glue on, they have whatever, yeah, you don't get it in a pure form. And therefore, finally, the collection of even small magnets, the collection of magnets out of applications where they have contaminations with other elements, which are making a bad magnet, finally, if you don't get rid of, will be expensive. Therefore, recycling will be always more expensive than to use virgin material. Yeah, therefore, just from economics, recycling will not be the way. From environmental, of course, it makes sense always not to go just for new virgin material and to make more scrap. Yeah, it makes sense to use it, but we need support from law, from legislation, that people have to collect it. Like with cars today, it would be much more cheaper to throw your car in the next lake. Yeah. Instead of working up. Yeah, but it makes sense. Yeah. And that will be the same for the rare earth. Therefore, recycling, there are a lot of institutions working on. We have technologies, but it will be more expensive, and therefore that is the thing we will need help from politics to make it. And it will come, definitely. And if you see there are applications like the wind generators where you have 4 tons at one place, that makes sense. Yeah, of course.
And it's the same grade, so you don't mix up grades if you.
Therefore, there is no problem. If you go for the cars, it's even a little bit more complicated, but we have legislation that the cars have to be worked up. Therefore, the magnets will be part of this. In this case, the legislation is even today helping to get the material available. In many other applications, there is no support. But recycling will come, but we need help.
But I could also just a comment. If I take my phone and I look at the magnet, they are maybe 1 or 2 gram magnets, and just to remove them from a phone will take minutes, and spending manpower or a robot to do that. I think it will cost more than the price for the raw material because very often magnets are so small.
Sure. That is exactly what I said. To collect the materials and to work it up will be expensive. Just some selected volume application will be sensible to do it. And even then, it will still not be the way to make a cheap magnet out of it. If it's a really cheap magnet, it's a poor magnet because you have all these additional elements you don't want to have. Carbon, for example, is a magnet killer.
Yeah.
If you have too much carbon in a volume of maybe 1%, it's killing your magnet. And all these bonded magnets, they have a lot of carbon. How do you want to get the powders out of these?
Yeah, yeah, it's difficult.
That's it. Yeah.
Thank you, Bernd.
You're so welcome.
I am
Was
really
enjoyable.
looking forward to meeting you in mid-November.
Yes.
When you come here and visit us. I enjoyed the conversation. I'm really looking forward to learning more about your new Indian adventure.
Sure. Yes.
Yeah. But
it's interesting to me the same way, and it is really an activity which makes sense, absolutely sense to all of us to support these activities. And India is a country with a lot of people. They need help. They need some industrial support to use these resources they have available. Therefore, I think it's not only our advantage, it's even our responsibility to support these people.
Yeah.
We did use them for many hundred years in a bad way. Therefore, let's pay back.
Good idea.
Yeah.
Thank you, Bernd.
You're welcome.
If people are interested in learning more, are they able to contact you?
Sure. Very easy. B.Grieb, Grieb, at ppm-materials.com.
Perfect. I'll also put your email in the last notes of the video.
Okay, good.
Wonderful. Thank you.
Thank you. Enjoy the day.
Yeah, you too.
Yeah, thank you. Bye-bye.